Hello everyone, welcome to our work on holistic transfer to rank for top M recommendation. I'm Wan Qima, a postgraduate student from Shenzhen University. This joint work was done with Xiaoxiao Liao, Wei Dai, and our supervisors Weike Pan and Zhong Ming. Now let's look at our problem. In our study top M recommendation problem, we have a set of rating records. Our goal is to generate a personalized candidate list for each user from the set of uninteractive items. There are two specific challenges, including how to adjust the uncertainty of the user's preferences beneath the examination behaviors and how to adjust the inconvenience of the 2 or 3-stage training and prediction procedures. To address these two challenges, we propose a holistic transfer learning framework and two instantiating algorithms, including a model-based one and a neighborhood-based one. We address the first challenge of uncertainty by making use of each rating score as a weighted confidence. We address the second challenge of inconvenience by developing a holistic one-stage solution. This table shows some notations. These are some words relevant to us. Tall and coffee tall are two closely related words. They both need step-by-step training and prediction. In order to elevate this problem, we aim to integrate these three steps into one holistic framework. BPR is a basic component of our HOTO, and this is the objective function of BPR. This is our illustration of our HOTO. We convert the rating records to three different views of users' behaviors, including examinations, scores, and purchases. But instead of designing a 2 or 3-stage solution like tall and coffee tall, we propose to combine these three views and obtain a one-stage solution. In particular, we first take the second view of scores as a weighted strategy for the first view of examinations, and then combine the weighted examinations and the third view of purchases in a holistic manner. Based on the proposed framework, we derive two specific algorithms, including a model-based one and a neighborhood-based one. Now let's look at the model-based one. In our model-based HOTO, we adopt the peer-wise learning manner in BPR to learn users' preferences beneath the examinations and the purchases. And we introduce a sampling trade-off to combine these two views of data. In order to exploit the second view of scores, we adopt a weighted version of BPR and develop a holistic objective function as follows. This is a weight for the user item peer. When the value of the sampling trade-off is between 0 and 1, our HOTO integrates three different views of behaviors in one single objective function. These are the gradients of the model parameters. This is the algorithm of our model-based HOTO. Now let's look at our neighborhood-based HOTO. The heuristic prediction rule for a user item pair in our household is as follows. This is a weighting trade-off, combining the left part of prediction based on the examinations and scores, and the right part of prediction based on the purchases. This denotes the weight estimated from the scores. When the value of the weighting trade-off is between 0 and 1, we exploit the complementarity of examinations, scores, and purchases, which is found to be better than equal to 0 and 1 in our empirical studies. Notice that we only need to generate the candidate list for each user once, instead of twice in total and 3 times in CoffeeTalk. For the model-based algorithm, we achieve a holistic solution from the perspective of a sampling strategy. For the neighborhood-based algorithm, we tend to expand the prediction rule of typical collaborative filtering methods. We conduct experiments on 3 public and widely used datasets, including Movie Runs 10 Million, Netflix, and Book Crossing. This table shows the statistics of the 3 processed datasets. These are the baselines used in our experiments. This is the setting of some parameters. We adopt 5 widely used metrics, including precision, record, F1, NDCG, and one-core. These are the experiment results of the model-based methods and the neighborhood-based methods. We can see that the 2 algorithms of our household achieves the best performance across the 3 datasets. Here are some other observations. We also conduct other experiments to verify the effectiveness of our household. In conclusion, we propose a novel solution called household for top-M recommendation. We derive 2 instantiations of the generic solution, including a model-based version and a neighborhood-based version. Empirical studies on 3 public datasets show that our household achieves very promising performance. For future work, we plan to develop a deep learning and ensemble learning-based one-stage transfer to rank solution, and we are interested in designing new perspectives and fusing different types of users' behaviors. Thank you for your listening. You are welcome to send us an email if you have any questions.